Good afternoon, everyone. Thanks for being here. I normally thank the audience for being here and listening and taking the time to listen, but I guess today instead I should thank you for caring, so thank you for caring. Today, indeed, I'll be talking about space, and I'll be talking about sustainability. So my aim for this afternoon is to share a little bit of my passion about space. But before I start that, just a small story. When I was a little girl, I was reading lots of books, and there were two, let's say, picture books that I enjoyed very much. One was a book about animals, The Animal Kingdom. I love that book, still love animals. The other one was actually a book about the universe that my parents had given to me when I was very small. It had pictures about the different planets, and I was looking through this book. And I never thought that I should become active as an engineer or be active in space. Many years later, I realized that my fascination with space started then, already back in the day when I was small. And I entered space because of that fascination, but when I then started being active in space activities, I actually discovered that space is a lot more than that fascination that pulled me in the first place. And hopefully I'll be sharing some of that today. So, Anna very kindly introduced me. I actually come to you today with two hats on, if you will. On the one hand, I'm professor at the university. On the other hand, I'm CEO of a startup. And I'll be bringing things that we do both from a university perspective as well as a startup perspective to push space forward. Just very briefly, at the chair at university, the chair is called Space Mobility and Propulsion. Why space mobility? I actually see space as like the fourth dimension, right? So we move on Earth, we move through sea, we move through air, and we move, and we will move more and more through space. So that was my purpose of calling the chair Space Mobility and Propulsion. Why? Because without propulsion, we can't actually move to anywhere, right? And what do we do at the chair? We look at democratization of access to space, so making sure that space is accessible to anyone through new technologies, especially propulsion systems for access to space, so in the launchers and big rockets. Then we look at in-space propulsion. In-space propulsion is a topic that we'll be looking at again later today, and I'll be telling you how we also try and make these propulsion systems a lot more intelligent. So I'm an engineer, I love machines, but fundamentally machines are a piece of hardware. I say they're like the muscle, right? And we need to make these machines a little bit more intelligent, so we also bring AI, so intelligent propulsion machines is another topic that we look at. We also try and look at breakthrough innovation, and we do testing for startups. One of the biggest challenges that startups have in the space industry, especially when it comes to hardware startups, is that it takes a lot of investment to do testing, for example, of propulsion systems. And when these startups go to VCs and say, hey, I have a new cool idea, the biggest challenge they have is actually building that infrastructure and being able to test. So as a chair, I thought, why don't we put the infrastructure that, after all, the government is financing through research to actually support these startups so they have a lower barrier to entry. So that's me at the chair. What about the startup I told you about? I'm CEO of Neurospace. Neurospace is a small company. We're 3 years old. We're about 30 people, and we support 300 satellites. And what do? We actually support them in understanding how to avoid collisions in space. And I'll get back to that. Some of these customers are already on board with us, so I'm very happy to say that we are getting to commercial sustainability, which isn't a given for space startups at such an early stage. So I was telling you at the beginning that I was fascinated about space and the stars, and I don't know how many of you in this room feel attracted to space because of this. This is an image that was taken by the James Webb Telescope. And what it actually shows, if you see those round circles, the curves, that's called microlensing. That's when gravity bends light. And that's, as I said, one of the earliest images that was taken through the James Webb Telescope. Another thing that fascinates me absolutely, and I think many find it fascinating as well, is exoplanets. Exoplanet research is also being done by the James Webb Telescope, and they've discovered so many planets which are like our Jupiter, like our Neptune. Some are actually similar to the Earth as well. And if they're similar to the Earth, so that means they're rocky planets, and in their so-called habitable zone, What does that mean? It means that they're in a zone where there's liquid water, because that can sustain life the way we know it. Then there's a chance that indeed these planets may have life again as we know it. Super fascinating. James Webb Telescope, huge, weighs 6 tons, 20 meters long, 14 meters in diameter. It has a 6-meter diameter mirror. Do you see the shades right here? This complexity is all needed to keep the mirror and the scientific instruments cold, so that they can do excellent science. The International Space Station, I'm sure you've certainly heard of, another big beast, 420 tons in space, 109 meters long, 74 meters deep or wide. This is all infrastructure. These elements are the elements that are most visible about space, and again, things that I find are absolutely fascinating. I don't know if you've ever heard of the mission Bepi Colombo, mission going to Mercury. Why Mercury? I mean, of course, we look at all the planets, but what's so fascinating about Mercury? Mercury is a planet which is more or less the size of our moon, but has a magnetic field. Our moon doesn't have a magnetic field. Why? We don't know yet, so we're going to try and figure that out. But Mercury is also in a gravitational lock with the sun, meaning that its rotational period, because it's so close to the sun, is actually it's in harmonics with the sun and with its orbital period. Again, very fascinating. What I very much love about this mission is what I discovered actually, again, going to visit the manufacturers of the solar panels. Now, I'm sure some of you have solar panels at home or want to put solar panels at home. And of course, we all know that to make solar panels efficient, the closer you get to the sun, the better it is. And then, of course, if you point them at 90 degrees, that's even better. But these solar panels are really, really huge. And I was asking the manufacturers, why are these solar panels so big? We're actually going towards the sun. Shouldn't they be smaller? And they said to me, yes, good point, but the closer you get to the sun, the hotter it gets. And if you're pointing the solar panels at 90 degrees, they're actually going to partially melt away. So we have to point them at 30 degrees to make sure that they don't get too hot. And so obviously if you're pointing them at 30 degrees, you're decreasing the efficiency, and then they get larger. Again, this is a European-Japanese joint mission. Super fascinating. Well, very complicated orbital parameters around it, but we'll find out soon what the secrets of Mercury are. Something also quite interesting are all the missions that we've seen that have gone to Mars. Skycrane is something that NASA developed in order to land on Mars. There's been quite a number of unsuccessful missions landing on Mars. It's quite hard. And Skycrane, what it does, it just basically deploys rovers by hovering at a distance from the surface and then just deploying the rovers so that they can land safely on Mars. Another thing which I personally find very interesting and fascinating was Ingenuity, a small solar-powered helicopter, the first helicopter on another planet. Okay, so this is all very fascinating. You say to me, Chiara, yes, it's true, but what does this have anything to do with us? I mean, it's exploration, it's Mars. And if you're not super fascinated about knowing where life comes from, then okay, I can understand your skepticism. But we found out about the greenhouse effect by looking at other planets. We learned about the greenhouse effect by observing Venus and understanding what's happened to Venus as a planet because of gases within the Venus atmosphere. So exploration and exploration of our solar system actually helps us understand our planet and help us improve also our understanding of how climate works on Earth. But indeed, space is infrastructure, right? And if we look at the kind of infrastructure it represents, we have launch segment. So obviously the part that brings satellites into orbit. So rocket launchers, here we see Ariane 5, which is no longer being operated, hopefully to be soon replaced by Ariane 6 later this year. We have a ground segment. Nobody ever talks about the ground segments because it's boring compared to the launch segment, but they're very important, big antennas that are necessary to track the satellites in orbit, communicate with them, give them commands. Why? Because these satellites aren't completely autonomous yet. We'll get to that later. And then, of course, we have the space segment. And the space segment fulfills different missions, responding to different requirements. They look different depending on what we're trying to do. Here we see a satellite which is for telecommunication purposes. These are some Earth observation satellites that we have in orbit. They're called the Sentinel spacecraft, been financed by the European Space Agency and the European Commission to generate different types of data so that we can extract intelligence out of it. So what I'm trying to say is that space indeed is an infrastructure, is an enabler. We shouldn't see space as just this fascinating thing, but it is, as I said, indeed an infrastructure. But it enables what? And it enables the part that we perhaps know less of, which is the end user segment, right? The precision farming. So being able to precisely farm land to understand exactly what kind of crop rotation that we have to do. Navigation with your mobile phones. I certainly use it every day, trying to understand where you are when you're backpacking. And all of the things that I've shown you before have some dimension that link back to the end user, as we call it. The International Space Station, we do lots of science on the International Space Station, from molecular biology, gravitational biology, combustion, fluid physics, material science, trying to understand how single crystal metals or materials are better than multi-crystal materials. And we also do research on genomes. One interesting anecdote, NASA has 2 astronauts, which are twins. They sent one twin to orbit and they left the other one on ground. I don't know which one was the more lucky one, but what they did is that they looked at the chromosomes of these 2 twins and they realized that the ends of the chromosomes of the twin that was in space actually changed in size compared to the twin that remained on ground. And what we know is that the ends of these chromosomes are actually linked with aging. So somehow we haven't found the solution to eternal life, but somehow we're understanding the link between things. So again, putting even astronauts in space is very important to understanding human physiology, because why? They're then experiencing different conditions that we don't experience on Earth. Telemedicine is another extremely important topic, where we're using telecommunications to provide medicine support to people that don't generally have access to it, through ubiquitous communication and, I said, medicine services. Telecommunications and global navigation can help us navigate when we are in aircraft better, so that we can better plan our routes over less populated areas. In the meantime, we know as well that somehow we can also hinder, through careful planning, the contrails, which also have a huge impact on cloud formation and which again impact our climate. Okay? And these are all things that we can have through space-based services. Space also helps tiny insects. I have bees at home. Actually, I'm a honey producer, so this is an important topic to me. How do we connect space to insects? We can actually check insect population and cross-check that with the way we're using land. Is it farmland? What kind of crops? And we know that biodiversity is not just climate change, which is an issue. We know that biodiversity is another issue, right? So understanding how insect population are evolving and what kind of pressures they're exposed to can also help us better understand and better plan how we use farmland and greenery in general. Another example I like to bring always is there's actually 50 so-called essential climate variables. These essential climate variables, they track different things. They don't just track climate, but they, for example, they track sea ice, sea level, sea surface temperature, ocean color, salinity of the oceans, greenhouse gases, ozone. And these 50 essential climate variables help us understand better how our climate evolves over time. Of these 50 essential climate variables, more than half can only really be tracked by space, through Earth observation-based spacecraft. Again, contribution of space to understanding our home world. Another thing which I, for example, didn't know and discovered only some years back, we actually use Earth observation satellites to continuously monitor our oceans. Why? Because oil spills happen actually quite regularly. Generally in the news we hear about the big catastrophes. Ships tend to lose some oil, and sometimes they also do some funky business, illegal stuff, because they're cleaning when they're not supposed to. We can actually see this, and by that we can do 2 things. Obviously we can reprimand those that have done something wrong, but we can then intervene a lot faster. Another thing is, of course, I don't know if you knew, but shipping transport represents about 85% of international trade by tonnage. So keeping a good eye on shipping routes is extremely important. Something called Automatic Identification System, AIS, is a service which we provide using space-based services by where we track ships and where they are. They send like a beep. And they're supposed to, they have to do this, right? What you see here in red are the most traveled routes. Okay, so basically black is where there's no ships. And if you compare then images that you get from Earth observation satellites and this kind of information, you can actually see ships that are not sending in their information. And if they're supposed to send this information and they're not doing it, then you know they're up to no good. And this is actually how a hijacked ship was sort of discovered and tracked several years back by combining radar images, satellite radar, with IAS. They were able to track back a ship that had been hijacked. But there's more things that we should be doing in the future. One of my favorite things to think of is indeed what kind of new services can we come up with. Prediction of volcanic eruptions is something people are working on, and I'd love to see happen. We can actually measure the changes in sort of how the Earth breathes, the changes in altitude of the surface, and by that, if we're looking and monitoring volcanoes, we can certainly understand if there's something happening soon. Something closer to home for those of you here home in Germany, we know that there were floods some several years back that could have been catered for a lot earlier. Prediction of floods. This is something we can certainly support with Earth observation. Looking into the estimation of how much solar energy we can produce by putting solar panels and such on buildings is another thing that we can be working on. Another example which I find extremely interesting, it has more of an economic dimension. I visited a company some years back and they were telling me, we take images of harbors and we check how many ships are on these harbors. And then we connect the images of these ships to the type of ships that they are and the kind of products they have on these ships. And then we look at the stock markets and the cost of these products on the stock market. And then we connect the time between it will take for these ships, depending on the queues, depending on the processes times that we have in the harbors, on how long it will take for this produce to be injected into the market. And then by that, we can actually tell how the cost of these products are going to evolve on the market over time. And then we can support people in deciding whether to invest or divest into produce. Again, it may be not benefit to climate change, but it certainly has an economic impact. Other example, the same company was providing support to oil and gas field companies because they wanted to check upon each other and see how far they were advancing on building that infrastructure to understand if they were still having a competitive edge over their competitors. So we've seen many examples on how space itself is a market, right? How there's infrastructure behind it that provides services, and these services bring some benefit, either to other sectors, to us as humanity, and to the planet. A recent report actually was brought out, expecting the space economy to grow to $1.8 trillion by 2035. These numbers are actually up from an earlier analysis which said that space would grow to be 1 trillion in 2040. So these numbers are growing. Of course, it's a bit of hocus pocus because we don't exactly know what's going to happen. But these are very positive numbers, right? And what they do is they actually split in classical space activities, so what I showed to you, the launch segment, the ground segment, the satellites themselves, traditional services that we provide. And then they talk about additional services that space will be providing that other sectors will see it advantageous for themselves and will also go into developing. And the average that they say is that the sector is going to grow at about 9%, as I said, over the next decade, which is quite significant. Now, with this growth, with more and more sectors that are seeing space as an advantage, of course, there's also a lot more launches being made. And in 2023 alone, if you see this plot, it actually shows the number of launch vehicles or launch attempts that have been made since the start of the space age in 1957, and we see where we are now in 2023. There's a number of launches that have been made over the years, and we have reached record heights with 223 orbital launch attempts this year alone, last year alone. And why do we say launch attempts? Not because, of course, not every rocket is successful in launching. But again, this means, as I said, that space is a sector that's growing, but it also has its challenges, right? And we'll talk about sustainability of space itself in a second. Now, before I go on, just sharing with you that, of course, if we look at the distribution in 2020, for example, and then 2023, we see that let's say the distribution of launch attempts has changed quite dramatically, right? So in 2020, we had US and China on par, and now we see in 2023 that there's been a significant increase in US launch attempts, and that somehow Europe is like this tiny little green thing right here. But okay, let's move on. Space is for humanity. So yes, there's been significant launch attempts. And what has been launched to orbit? So you've seen the James Webb Telescope. That's like big launch infrastructure. But there's been an increasing trend toward also smaller spacecraft. Why? Of course, they are more economically viable, right? If you're a startup, you don't necessarily have the availability of launching hundreds of millions of infrastructure into space, a satellite into space, but you can launch maybe a CubeSat, which costs 1 million or so, or even less. Now, what's the advantage of CubeSats? As I said, they're more economically viable. What's the disadvantage is that until now, many of them didn't necessarily have propulsion system on board. And that's a bit of a problem when it comes to sustainability, and we'll get to that in a second. So of course, as I said, to make all of this happen, we have to get into orbit first. Again, Ariane 5 launching. And you know how they say it's rocket science? Well, if you want to be a rocket scientist, you just have to remember this equation. There's all that's to it. Delta V, so the energy that you have to impart to a vehicle or a satellite for it to get into orbit is actually equal, of course, to the end velocity minus the initial velocity being 0, of course. And that's equal to the effective exhaust velocity of the hot gases that we've seen coming from the rocket times the natural log of the mass that it has at the beginning divided the mass that it has in the end. Basically what we're saying is we're trying to convert propellant into velocity. We're taking propellant, we're combusting that, we're creating thermal energy, and then we take that thermal energy and we convert it to kinetic energy and we boost something into orbit. Okay, that's all there is to rocket science. And of course we are trying to aim to get at different orbits. And these different orbits have different characteristics to them, right? So for example, we see the blue one, LEO orbit. In low Earth orbit, so LEO, we're not so far from the surface of the Earth. If you see the smallest number, it's 200 kilometers. That's actually closer to Munich where I teach, so that's not really far. But there, as I said, there's lots of energy that we have to impart to these objects to get into orbit. We put Earth observation satellites in low Earth orbits. Why? Because we're trying to look to the surface of the Earth. We want to have high resolutions, and therefore it's better to put them in low Earth orbit. In geostationary orbit, for example, we put telecommunication satellites. Why? Because in geostationary orbit, the orbital period of a spacecraft is 1 day, which is the same as the rotational period of the Earth as it moves on its axis. And so basically what we have is that the satellite remains stationary over the same point of the Earth. And that's why it's good for telecommunication purposes, okay? Now, of course, the energy that we need to put these objects into orbit has some implication also on the energy that we need to bring these objects back down, right? And because we don't want to leave things into orbit forever, because that's not very sustainable, then we understand that when we look at the economies of things, if someone puts an object into orbit, it will cost X, depending on the launch vehicle they're on, but it will also cost something to take this back down. And that's part of the problem that we have today in space. Okay, so again, in order to understand the physics behind it, if you're not much of a technical person, imagine being in Newton's cannonball, right? And trying to understand what kind of velocity that you have to be imparted with if you're in this cannon in order to continuously fall into the Earth without actually touching the surface. And that gives you the energy that we need to get into orbit. Again, just to give you an idea, We were talking about altitudes of 300 kilometers, for example, or 200. The kind of velocity that objects have to have in orbit are about 7 to 8 kilometers a second. That's huge, right? So to put this in relation to things that we know, just giving some ideas, if we take a Formula One car, the engine more or less has about 850 PS horsepower. If we look at the engine of a jumbo jet, we're at about 18,000 horsepower. If we look at the Vulcan 2 engine, which is the central engine of Ariane 5, it has 4 million horsepower, right? So again, this is to give you a feeling for what we're looking at. And again, this is the kind of energy we need to get into orbit, but it's the same kind of energy that we need then to bring things back down. Now, once we're in orbit, there's all sorts of challenges that we have in orbit, right? And you may have seen that recently we're going through a solar high, solar maximum, and I don't know if you were lucky enough to see auroras. I live not so far from Darmstadt, actually, and they were visible as far as Darmstadt. So that's great. But where do these come from? Indeed, they come from the sun that's very active on an 11-year period, but spews lots of energies in our direction. And what happens is that these particles interact with the magnetic field of the Earth, and the particles enter the atmosphere, and these ionized particles then, when they enter at the poles, they cause the auroras. And as I said, there's an 11-year solar cycle, and I'll tell you in a second why we care about this at all. And these coronal mass ejections, as you see them here, they can be quite significant. This has become more and more important for our societies today. Why? Because we're becoming more and more digitalized, right? So if there's surges in our power grids, they can cause blackouts. And in fact, there was indeed some significant power outages across the world just last month. Now, I mentioned to you, indeed, that putting all of these objects into orbit means that somehow we also have to consider what happens to these objects once we don't use them anymore, right? So when your car is not functioning anymore, you have to bring it to someone that will discard it. Well, so far we didn't have any legal regime in space in place in order to really take care of that. So we have a situation now where we have nearly 40,000 objects in orbit which are larger than 10 centimeters. We have about 1 million objects that are larger than 1 centimeter. And we have over 130 million objects which are larger than 1 millimeter. Now, I've shared with you the velocities of these objects, right? Remember the 8 kilometers a second? Now imagine that something's traveling at 8 kilometers a second and is hitting you at 8 kilometers a second. No matter how small it is, it's bound to hurt, okay? So now comes the problem. We have lots of objects in space, and these objects pose a threat to other assets. So we want to have telecommunication services, we want to have Earth observation services, we want to have all of these benefits, but at the same time, we have a risk to these objects. What this plot shows you is, again, since the beginning of the space age, the increase in the number of objects that we have in space, both active and non-active. The dark blue is the payloads, that's the satellites, the ones that are active, but everything else is non-active objects. And when they're not active, means that they're not maneuverable anymore. And if they're not maneuverable anymore, then somehow, if something is coming at you with 8 kilometers a second, then you better move out of the way. And that's, if you will, part of the problem. Now here we see the altitudes on the y-axis and the density, meaning the number of objects that we have at these altitudes. We see the International Space Station is about 400 kilometers, so it's still, let's say, in a safe region. But then we have the Starlink satellites that we've heard about, and there were a couple of incidents in the past that aggravated the situation significantly. What causes this so-called space debris? And again, here you see the same image, but zooming in. In 2007, there was a weapons test. So China, but China's not the only country, unfortunately. I wish it was, because then it would make the problem smaller. China decided it was a good idea to just hit another object. And so they did a weapons test and tried to destroy one of their own satellites, and they did. And of course, that caused lots of pieces of debris in orbit. Then we had a collision of 2 satellites in orbit that hadn't been predicted, that didn't move out of the way, and that caused another step increase that you see. But we have other, as I said, sources of space debris, including fragmentation events. What are fragmentation events? If you put a spacecraft into orbit and you have batteries, for example, or a propulsion system, and you don't passivate it, they can actually explode over time because they heat up and they can actually explode. So again, we have to take care. How much does it hurt? This is a test that was done by the European Space Agency, and a small sphere of 1.2 centimeters was sort of projected towards an 18-centimeter slab of aluminium, and you see how big the crater is. The object was traveling at 6.8 kilometers a second. Now, satellites aren't made of 18 centimeters of aluminium slab, okay? So again, this can fundamentally destroy or cause significant irreparable damage to a satellite. And that's actually what happened in, I think it was 2010 or so. Sentinel-1A, so an Earth observation satellite, the European Space Agency was operating the satellite and realized all of a sudden, we have less power coming from the solar arrays. And so they turned on the cameras and they saw that there was a sort of a darker spot on the solar array. And they compared it to an earlier image and realized indeed that it had been impacted by space debris of 1 centimeter. So now, what can actually happen if indeed there's a collision of two spacecraft? So in 2009, there was a collision between two satellites, Iridium and Cosmos. And what you see was, you saw the two original satellites collide, and now accelerated, you see this whole cloud of objects and how this cloud of objects distributes, not only in the orbital plane of the original, let's say, mother object, but then how over time, because of different disturbances that we have, they actually go and pollute other orbits as well. So the problem of space debris is fundamentally an issue. Why? Because when we have a little object, it's hard to track. We can't necessarily see it from the ground, but it's also very hard to understand where it is and where it evolve over time. Oops. Okay. Why? I showed to you space weather. And if we look at the impact of space weather on the density of our atmosphere, it has a huge impact. We have here a plot which shows you low activity, so low solar activity, for example, during the night, and high activity, and you see how much the density of our atmosphere changes because of the impact of the sun. Now, what is the issue here? Imagine being one of these two satellites. So we have a chaser and we have a target. And we know that the orbits of these two satellites are going to intersect at some point. Okay? The problem is that, because of what I showed to you, we don't exactly know where these objects will be. We have a rough idea. And what we do is we depict these satellites as ellipsoids. Okay? So we say the blue satellite is here, but it could be anywhere in this ellipsoid. And the pink satellite is here, but it could be anywhere here. Why? Because we're trying to predict ahead of time. We try and predict 4, 5, 6 days ahead. And because of the changes in atmosphere, density, et cetera, and because of the other perturbations, we can't know exactly, right? So that's the difficulty. And imagine being a satellite operator, and now somebody's telling you, there's going to be an object that's going to come and hit you. Are you going to move? You don't know if you should move or not, right? It's easier not to move. But that could go wrong. Now, the problem that we have is indeed there isn't too much of a legal regime around space. We have guidelines from the UN. We have a so-called Interagency Space Debris Coordination Committee, which tells us what we should be doing to behave well, to maintain space clean, so that, again, we can continue providing services. But none of this is binding, okay? Original documents stated that we should leave objects in orbit for a maximum of 25 years. Now imagine for a second that your car stops working and you just leave it on the side of the road for 25 years. I don't know, but I think that's a bit too much. People have started rethinking this and now have decided that 5 years is a lot. Personally, if you ask me, even 5 years is a lot. At this stage, it's very hard for us to come to agreements between nations. I think you're all aware of the very complicated geopolitical situation that we have. Could you imagine all countries of the world signing something saying, yes, we will all agree to removing our satellites from orbit as soon as they don't work. We will all agree to not performing satellite tests, so actively destroying satellites in orbit. I don't think that's going to happen. Our hope are two things. One, national legislation, and we see some countries taking the lead. For example, France has in its national law that if someone launches from French territory, they actually have to deorbit what they launch after they launch it. Fantastic. Germany, unfortunately, we still don't have a space law. Hopefully we will get to it. Okay. And some of these guidelines, they actually define two so-called protected regions. And there's two protected regions that we talk about. One is the low Earth orbit, and you saw how many objects there were. And the other one is the geosynchronous orbit. Low Earth orbit, because again, we have the International Space Station, because there's many objects in there, because it's very attractive from an economic point of view. And geosynchronous orbits, because again, it goes back to what I had mentioned to you before. It takes a lot of energy to put objects into space. This is where we have most of the telecommunication satellites, and if we populate those orbits, then we won't be able to use those orbits anymore to provide further telecommunication services. So we try and protect those regions. Again, I find this fantastic. I think we should be doing more, because fundamentally we should protect all regions. So, sustainability. Something's happened to the Earth, by the way, on this slide. For some why it got squished. Forgive me for that. But when I talk about sustainability, for me, there's various elements which are important. The environmental aspect, so I told you about the number of objects that we have in orbit. We have to get rid of those for sure. But there's also an economic dimension. We can't really push for sustainability if it's not economically viable. And that's also where I hope that startups and other companies understand the importance and will act before we have an international regime in orbit. The other dimension for me is also scarcity and resources. I love this planet. I don't believe that we should necessarily be fueling space activities just from resources on Earth. The universe is huge. There's so many resources in orbit. Can't we use resources that are also in orbit? And I think we should. And we'll get to that in a second. And of course, why? All of this is important because fundamentally it goes back to what I was saying at the beginning. There's so many services, climate change, biodiversity, telecommunications, telemedicine, all of that. So we need to guarantee the safety and security of those assets that we put into space. And we can only do that if we make sure that there's no collisions and that these orbital regimes are clean. So the space community is working very hard, and there's various elements that we're looking at. Eco-design. So how can we reduce the impacts of manufacturing, producing, and launching? How can we manage the end of life of satellites, for example, removing objects from space, but not only? And how can we think of a future, indeed, where we're servicing in orbit? Here it says active debris removal, that's certainly one of them, but how can we do more? And for me, all of this and sustainability is the basis for a future in space economy, right? So today we're looking at fleet management. So we're managing our satellites, we're managing our fleets of satellites. We have done some maintenance into orbit. We have already done life extension. There has been a satellite, and I have an image coming up. There is a company that sent up a propulsion system to extend the life of a telecommunications satellite in orbit. But can we think of refueling, manufacturing, assembling, recycling in orbit? We must, we should, we are. And that, for me, is, if you will, the unifying vision that I have. At some point, we will be using resources in space. That's only natural. It will extend our economic regime to space. And it will also enable us to use resources that are not limited to our tiny blue and fantastic dot. So this is the image I was telling you about. What we actually see is a geostationary orbit satellite that was serviced by a mission extension vehicle, and we see here the vehicle docking onto the end of the satellite. And what it did is it provided propulsion needs for another 10 years of mission, right? Because when you have a satellite with a propulsion system, once you don't have any more propellant on board, that's it, end of story. right? And that's a bit of a problem. So again, what is the vision? The vision for me is self-sustaining autonomous activities in space, where we are somehow extracting and distributing resources that we get in space. We distribute these resources across multiple spacecraft or other things that we do, and we use them for autonomous and sustainable operations to provide all of those services that I was mentioning. But for this, we have a number of challenges moving forward. Some of them are technical, of course, some of them are of legal nature. So let's just look at some of these aspects. Spacecraft autonomy. Today, when you have a spacecraft in orbit, what you generally have is someone sitting on ground, which schedules commands and tasks for the spacecraft, sends it on orbit, and these functions are then performed. Okay? But we want to go to a complete goal-oriented operation. So basically, the spacecraft knows that it has to perform X mission, and it will replan what it does in order to fulfill that, including surprises or anomalies that could come its way. We're not there yet. We have some adaptive so-called event-based operations on board. Some examples of this. There was a Deep Space One in 1998, which was tested, and this was basically taking over some of the spacecraft functions to fulfill, as I said, missions operations. Another experiment was done about 10 years later with the EO1 autonomous science craft experiment. What did this mission do? It was actually flying over a volcano, noticed the heat signature, and then thought, there's something interesting happening there. Let me take the picture next time I go over it. Okay, so this spacecraft understood that there was something that was valuable to measure and decided to, as I said, adapt its missions operations accordingly. We did another experiment through the European Space Agency some years later as well. And you can imagine that the first interesting element of autonomy could be, I'm an Earth observation spacecraft, I'm flying over a region of the Earth, and I'm actually interested in looking at the delta of a river and understanding what biodiversity is doing in that region, if it's changing or not. But it's very cloudy, and I've just taken an image of clouds. Clouds are interesting, but not interesting in this case, and so it decides not to take an image or not to beam it back to Earth, right? Again, very, very interesting. So what are some of the pains that we have on our way to self-sustaining and autonomous space activities? The first one, indeed, is space propulsion. I told you, not all spacecraft have space propulsion, and some of them that do have complex propulsion systems which are based on hydrazine. Hydrazine is a bit of a toxic propellant, so not exactly green, but it's storable. Okay, so the advantage is you can store it for many, many years, which is great because then you can use it in orbit, and it has a couple other advantages. One of the disadvantages is that when you're operating with it, you end up running around like a Michelin man or woman because you're in a suit to make sure that you're not in contact with it. So we want to fix this problem. And what are we doing at the university? We're looking into so-called water electrolysis propulsion. So our propellant here is not hydrazine, it's water. Water is, I think you argue, the cleanest of all possible propellants. You can actually drink it. We're actually using completely demineralized water, so it probably doesn't taste much, but still very clean. What do? We take the water, we send it through an electrolyzer. Through that, we split it into hydrogen and oxygen, and then we take this and we can use it, for example, and we can combust it in a hot gas thruster. Or we can take the hydrogen or oxygen and we can use it in an electric thruster, which has very high performance as well. Or we can use some cold gas attitude and control. So we're looking at the aspects of this, and we're looking into how we can optimize electrolyzer units. We're looking at here a cathode vapor feed system, where we actually have the water in its liquid form, which is then vaporized through a water barrier, and then we, as I said, split it into the two. The other thing that we're looking at is the thruster element right here, and we're trying to optimize the heat transfer properties that we have through the walls so that we can optimize how we combust the propellants and take, as I said, what we do is we take the propellants, we produce thermal energy, and then we convert that thermal energy into kinetic energy through the nozzle. And we're trying to optimize that so we can produce a propulsion system which has an even better performance than current propulsion systems. So we remove the pain of having bad, let's say, liquid propulsion or propellant systems, and we increase the performance. Now, the other pain that we have, again, is linked to all of these objects that we have in space, okay? And, you know, I said at the beginning that space sector is growing and that many sectors seeing it as an advantage. So there's lots of companies that are planning on putting even more satellites into orbit. I'm sure you've heard of Starlink, you've heard of Kuiper and Amazon. There's many more. And again, this is actually good news, but we need to take care of it. One of the downsides is, of course, because there's so many assets or spacecraft in orbit, the number of potential conjunction, meaning the potential collisions between these objects, is also growing, okay? And some of the costs associated with this is if you are a spacecraft and something is coming at you and you only learn about this in the very short term and you have to make an emergency maneuver, it may cost you about 25,000 euros. And if you're now a constellation operator and you have 100 satellites in your constellation, this may actually mean a loss of about 3 million euro a year, which is not so good, right? So we need to take care about this. Now, in 2014, there was another collision that happened, and 2 Iridium satellites were actually slightly damaged. And they actually reported revenue loss of $8 million. So again, it goes back to what I was saying. There needs to be also an economic pressure to act, and there is. Now, what do we know? We know that there's many activities that we can do. For example, we can dispose at the end of mission through either propulsion systems, but I told you that costs quite a bit. We can increase the drag. I mentioned that drag is something important, right? And that depending on the solar activity, the density of our atmosphere changes. So if we have high drag, we can actually take some of that energy away from the objects and can bring them back. Or we can do some active remediation, whereby we take objects that are in space and we bring them down. And that's actually quite important. There have been 50 objects that have been identified that we should be taking down. And if we do so, then the population of these debris and the difficulty that we have associated them is going to decrease based on how many objects per year we decide to take down. So I mentioned to you the fact that we have uncertainties linked to the position of where these objects will be. And again, imagine that you're in a spacecraft and you don't exactly know if there's going to be a collision coming or not. Then generally, the course of action is you don't move. Because if you move, that could also mean that you're putting yourself in harm's way. So as I was saying to you at Neurospace, what we do is we're looking at doing that. So we're trying to provide insight to satellite operators so that they can decide whether to move or not. We have a number of technologies that we look at. We look at data. Data is key. We bring this data together. We correlate the data together. We have AI and machine learning prediction models, and automation is also key. So different types of data. We spoke about space weather data. We use data from optical ground sensors and telescopes, radar. Each of these data sources brings benefit. There isn't a single, let's say, source of data that can tell you everything. We look at laser tracking as well. We look at the information of the satellites themselves, how big they are, how small they are, how the distribution is, do they have big solar panels, because that's going to have an impact on how they maneuver, et cetera, et cetera. And as I said, we also have AI and machine learning on board. We heard about AI and machine learning from the previous speaker, actually. Seeing it from an engineering point of view, AI and machine learning, or so-called cognitive technologies, are very important because they can do one of 3 things. Automation of processes. They can provide insights and recognize patterns where we as humans cannot. And they can also help us analyze, engage with customers, employees. This is the one, of course, that's been sort of going through the media the most with ChatGPT and the large language models, for sure. What do we do at Neurospace? We've developed, for example, a so-called taxonomy of resident space objects. What does that mean? I learned that people in northern countries and Scandinavian countries have, 20, 30 different ways of talking about snow. Fresh snow, old snow, snow that has just fallen, snow that is wet, snow that is not so wet. I don't know, again, I'm not from Scandinavian country, but this is exactly the same thing, right? The more you can describe and distinguish one object from another, one satellite from another, the better you can actually also understand how it's going to behave if it is exposed to certain external elements. So we've used AI and machine learning to understand what characteristics dominate the behavior of satellites in space so that we can better improve all other models that determine the characteristics of these objects. And we fed this information in order to provide satellite operators with autonomous collision avoidance information. So what you see again is two objects with a certain level of uncertainty. We tell them what the probability of collision is, and we tell them how they should maneuver it best. And what you see here, for example, is also another piece of information that we give them. You remember how I showed you the ellipsoids and how big they are? So key, again, is to understanding how these ellipsoids are going to change. And ideally, they're going to get smaller and smaller, and then fundamentally at the end, you know, okay, makes sense to move or it doesn't make sense to move. And we've developed a model that you see here, takes information that we have, here in red, and predicts the evolution of that uncertainty. So at the very least, the satellite operator knows that uncertainty is going to decrease. I can make a decision for sure. Uncertainty is going to stay very high. It's better if I just stay put because, well, space still is very large after all. So I've given you lots of information. The last thing I want to conclude with is a quote, one I like very much, from Arthur C. Clarke, which is, "If an elderly but distinguished scientist says that something is possible, he is almost certainly right. But if he says that something is impossible, he is very probably wrong." Thank you very much for your time, and again, thank you for caring.